Hi, I'm Janet Stramel. This is Integrating the Standards for Mathematical Practice into Your Daily Lessons. This is a two-part series. Today I'm going to talk through Standards 1, 2, 3, and 6. Part 2 will be next week, where I will be discussing the remaining Standards for Mathematical Practice 4, 5, 7, and 8. Just a little bit about me. I teach mathematics methods and the concepts of our elementary mathematics at Fort Hays State University. Fort Hays is in western Kansas. I also am a National Board Certified Teacher in Early Adolescence Mathematics, and I'm a former middle school mathematics teacher. I taught 7th and 8th grade math in Kansas and also Oklahoma. So thank you for being here today. Today, we're going to talk about, of course, the standards for mathematical practice, and you can see that they reflect what it means to do mathematics. No matter what your objectives are, the textbook you use, or the grade level you teach, the 8 standards for mathematical practice are a guide to good mathematics instruction. This session today will give you suggestions for incorporating them into your everyday mathematics instruction. And again, today I will cover Standards 1, 6, 2, and 3. When you read the standards for mathematical practice, you'll notice that each one begins with the 3 words, mathematically proficient students. Also notice how the standards are completely student-centered. Instead of teacher-led instruction for the majority of the class period, we want to facilitate meaningful discussions in your classroom and allow your students to drive the conversations. We want to motivate students to attack each task from their own angle. Allow your students to explore, discuss, and disagree with one another. They may fail, they may succeed, and they may fail again. But in the end, the vast majority of your students will become mathematically proficient. Also, you'll notice as you read the standards for mathematical practice that mathematically proficient students do not listen while we as the teacher give direct instruction. They don't just copy notes word for word from the board. They don't just memorize rules and procedures for solving a problem and then duplicating that later on. And students do not just sit quietly throughout the entire lesson. We want our students to have that discourse. So if you were wondering why I chose 1, 6, and 2, and 3 for today's presentation, this is why. Bill McCollum said that many of the processes and proficiencies in the individual practice standards overlap, and several may be used together in solving a problem or engaging in a task. Additionally, most of the practices can be applied to most of the content standards. In order to avoid doing nothing when integrating the practice and content standards, Dr. McCollum grouped the standards to bring a higher order of structure. So let's begin with Standards 1 and 6. Mathematical practice standards 1 and 6 relate to habits of mind, making sense of problems, persevering to a solution, and attending to precision. These principles define what all students must do to become proficient users of mathematics. Practice number 1 and practice number 6 serve as an umbrella for the other practice standards. In order for the other mathematical practices to be meaningful, the overarching habits of mind must be enforced. Mathematical practice number 1 ask students to develop that puzzler's disposition in the context of mathematics. Teaching can certainly include focused instruction, but students must also get a chance to tackle problems that they have not been taught explicitly how to solve, as long as they have adequate background to figure out how to make progress. Young children need to build their own toolkit for solving problems and need opportunities and encouragement to get a handle on hard problems by thinking about similar but simpler problems, perhaps using simpler numbers or a simpler solution. Mathematically proficient students make meaning of the problem and find entry points. They monitor their progress, continually asking themselves, does this make sense? And then changing their course if necessary. They understand various approaches to solutions and are able to explain their thought processes in solving a problem. Students are also able to stay with a challenging problem for more than one attempt. They try several approaches in finding a solution and learn from those previous solution attempts. Basically, you will find practice standard 1 in every math problem every day. The hardest part is pushing students to solve those tough problems by applying what they already know and monitor themselves while solving that problem. As a teacher, we want to give our students tough tasks and let them work through them. We want to allow wait time not only for our students but for ourselves, and we want to work for progress and that aha moment. Then the math becomes about the process and not about just one right answer. You want to lead with questions, but don't show your students how to work the problem. As teachers, we need to provide time and facilitate discussion in problem solutions. We need to facilitate discourse in the classroom so that students understand the approaches of others. As teachers, we need to provide opportunities for our students to explain themselves, the meaning of the problem, etc., to provide opportunities for students to connect concepts to their world. As teachers, we also need to provide our students time to think and to become patient problem solvers. We want to facilitate and encourage our students to check their answers using different methods, but not just using a calculator to check answers, and to provide problems that focus on relationships and problems that are generalizable. Mathematically proficient students are actively engaged in solving problems, and their thinking is visible. And what I mean by that is they're actually doing the mathematics, not just following a step or a procedure or a rule. Mathematically proficient students are analyzing givens, constraints, relationships, and goals, not just the teacher doing that. They are discussing with one another, making conjectures, planning a solution pathway. They're not just jumping into a solution attempt or guessing at the direction they need to take. Mathematically proficient students relate a current situation to a concept or skill they've previously learned, and they continually ask themselves, does this make sense? And by the way, I did retrieve this information from the Illustrative Mathematics website. It's just illustrativemathematics.org. So my first sample task that I want to share with you is from Illustrative Mathematics. Mathematically proficient students start by explaining to themselves the meaning of the problem and look for entry points. They consider analogous problems and try special cases and simpler forms of the original problem in order to gain insight into a solution. They monitor and evaluate their progress and change course if necessary. Older students, depending on the context of the problem, transform algebraic expressions or change the viewing window on their graphing calculator to get the information they need. Mathematically proficient students can explain correspondences between equations, verbal descriptions, tables and graphs, or draw diagrams of important features and relationships. They graph data and they search for regularity and trends. Younger students might rely on using concrete objects or pictures to help conceptualize and solve a problem. Mathematically proficient students check their answers to problems using different methods, and again, they continually ask themselves, does this make sense? They understand the approaches of others to solving complex problems, and they identify correspondences between different approaches. Additionally, as teachers, of course, we want to help our students make sense of problems and persevere in solving them. So here are some sample questions that you could ask your students. How would you describe what you're trying to find? Or what do you notice about? Or what information is given in the problem? Talk me through the steps you've used up to this point. What are some other strategies you might try? Or how else might you organize this problem or represent this problem or show this problem? Or one last one, how might you use one of your previous problems to help you begin? The standard for mathematical practice number 6 is attend to precision. Mathematically proficient students try to communicate precisely with others. They specify units of measurement, they calculate efficiently and accurately, and express numerical answers with the degree of precision appropriate for the problem context. Students can communicate their reasoning and solution to others, incorporate appropriate vocabulary and symbols, and label effectively in order to communicate and exchange ideas. The title, Attend to Precision, could potentially be misleading. While this standard does include calculate accurately and efficiently, the primary focus of this standard is precision of communication in speech, in written symbols, and in specifying the nature and units of quantities in numerical answers and in graphs and diagrams. In order to teach our students to attend to precision, you will want to push your students to use precise and exact language in mathematics. Our measurements should be exact, numbers should be precise, and the explanations must be detailed. One change I've made in my own classroom is to not allow the phrase, "I don't get it." Students need to explain to me exactly what they don't get or exactly what they don't understand and where their understanding falls apart. And then I can work through the problem with them when I know where they are and when they have verbalized their solution attempts. These are just two examples for mathematical practice number 6. Elementary students are able to solve problems and explain their thinking to others. In secondary, students can examine claims and make explicit use of definitions. As teachers, we want to facilitate, encourage, and expect precision in communication using mathematical vocabulary and terminology. And we want to provide opportunities for our students to explain and or write their reasoning to others. Students, in order to meet practice number 6, attend to precision, will use and clarify mathematical definitions in discussions and in their own reasoning, whether that's orally or in writing. We want our students to use, understand, and state the meaning of symbols, and we want our students to express numerical answers with a degree of precision. The standards for mathematical practice focus on the nature of learning experiences by attending to the thinking processes and habits of mind that students need to develop in order to attain a deep and flexible understanding of mathematics. Certain tasks do lend themselves to the demonstration of specific practices by students. The practices that are observable during exploration of a task depend on how instruction unfolds in your classroom. While it is possible that tasks may be connected to several practices, I will highlight just one practice connection at this time. So again, I've chosen a sample task from the Illustrative Mathematics website, and you can see that link there, illustrativemathematics.org. And if you go to the /practice-standards, you can see these tasks. The purpose of this task, called Valid Equalities for first graders, is to help broaden and deepen students' understanding of the equal sign and of equality. For some students, an equal sign just means compute or the answer is, because they only see equations in that traditional form of 3 plus 4 equals 7. So in this particular task, students must attend to the meaning of the equal sign by determining whether or not the left-hand expression and the right-hand expression are equal. This task helps students attend to precision, which is practice number 6. Many of these problems naturally lead to discussions of topics such as place value and properties of addition. So this particular task, Valid Equalities, helps illustrate mathematical practice number 6, attend to precision. Students use mathematical symbols correctly, and they describe the meaning of the symbols they use. In this case, they understand that the equal sign denotes that quantities on either side have the same value, and they use that understanding flexibly to identify and express equivalences. When crafting their explanations, they learn to communicate their reasoning by using precise mathematical vocabulary describing each quantity accurately. Even though the main focus may be attend to precision, this task also supports practice number 3, construct viable arguments and critique the reasoning of others, as well as number 7, look for and make use of structure, and we'll talk about those two later. So you did probably notice that these questions ask for simple true-false. It says decide if the equations are true or false. But complete solutions require a valid explanation. There are many possible explanations, so there is a variety of kinds of explanations in the solutions when you go to this website. For example, the first one you see, 2 plus 5 equals 6. Well, you know 2 plus 5 is 7, not 6, so that is false. But maybe a student would change the 2 to a 1 and say, I know that 1 plus 5 is 6, and then it would be true. So then your students are attending to precision. Another sample task also comes from the Illustrative Mathematics website. The task is about comparing freezing points. The problem says ocean water freezes at about negative 212 degrees Celsius. Fresh water freezes at 0 degrees Celsius. Antifreeze, a liquid used in the radiators of cars, freezes at negative 64 degrees Celsius. Imagine the temperature has dropped to the freezing point for ocean water. How many degrees more must the temperature drop for the antifreeze to turn solid? This task is appropriate for assessing students' understanding of the differences of integers. Because the task asks how many degrees the temperature drops, it is correct to say that the temperature drops 61 5/10 degrees, 61.5 degrees. However, some might think that the answer should be that the temperature is changing a negative 61 5/10 degrees, negative 61.5. Having students write the answer in sentence form allows teachers to interpret their response in a way that a purely numerical response would not. This task is most beneficial for a teacher to use to assess a student's understanding of differences of signed numbers. To best assess this understanding, the student needs to describe in context what must happen for the antifreeze to solidify, making sure to use clear, precise language when doing so, which is practice number 6. The teacher could use this task after multiple contextual and numerical rational number subtraction and addition problems using number lines, counters, or the prior understanding of rational numbers, which is developed in 6th grade. As the teacher, you could determine from this task if the student is starting to formalize the rules for addition and subtraction operations with integers through the interpretation of the contextual answer the student gives. And you will notice that the commentary allows for a negative answer as long as the student gives a clear and correct interpretation of that answer in the sentence that surrounds that number. Questions that you could ask your students to develop mathematical thinking that are related to practice number 6. What mathematical terms apply to this situation? How did you know your solution was reasonable? Explain how you might show that your solution answers the problem. Ask your students, is there a more efficient strategy? And how are you showing the meaning of quantities? What symbols or mathematical notations are important in this problem? You could also ask your students to test their solution to see if it answers the problem. And just a reminder, mathematical practices 1 and 6 are about developing habits of mind. Now for standards 2 and 3, and remember from Dr. McCollum's chart, 2 and 3 is about reasoning and explaining. Two is to reason abstractly and quantitatively, construct viable arguments, and critique the reasoning of others. That is 2 and 3. The standard for mathematical practice number 2, reason abstractly and quantitatively. Mathematically proficient students make sense of quantities and their relationships in problem situations. They are able to represent the problem symbolically and manipulate symbols. They understand the meaning of quantities and are flexible in the use of properties of operations. Mathematically proficient students can reason with models or pictorial representations to solve problems. They are able to translate situations into symbols for solving problems and convert situations into symbols that appropriately solve problems, as well as convert symbols into meaningful situations. Practice number 2 asks students to be able to translate a problem situation into a number sentence with or without blanks or variables, and after they solve the arithmetic apart in any way they wish, to be able to recognize the connection between all the elements of the sentence and the original problem. It involves making sure that the units in problems make sense. So, for example, in decontextualizing a problem that asks how many buses are needed for 99 children if each bus seats 44 people, a child might write 99 divided by 44. So after they calculate 99 divided by 44, they could get 2 remainder 11, 2 and 1/4, or 2 and 25 hundredths, 2.25. The student then needs to recontextualize, look at the context, and realize that it requires a whole number answer, but in this case, it's not the nearest whole number that they need. So successful recontextualization also means that the student knows that the answer is 3 buses, not 3 children, or just the number 3. In order to help our students reason abstractly and quantitatively, we as teachers need to provide a range of representations of math problems and math problem situations that encourages various solutions. We need to provide opportunities for our students to make sense of quantities and their relationships in problem situations. And we want to provide problems that require flexible use of properties or operations and objects. And we want to emphasize quantitative reasoning, which entails habits of creating a coherent representation of the problem. Consider the units involved. Attend to the meaning of quantities, not just how to compute or following a rule. And knowing and flexibly using different properties of operations and objects. Our students should use varied representations and approaches when solving problems. They should make sense of quantities and their relationships in problem situations. They should decontextualize and contextualize a problem. And our students should use quantitative reasoning that entails creating a coherent representation of the problem. Consider the units and attend to the meaning of quantities, not just how to compute or do the arithmetic. Again, from the Illustrative Mathematics website, I've chosen one problem. You can read it. In the barnyard is an assortment of chickens and pigs. Counting heads, I get 13. Counting legs, I get 46. How many pigs and chickens are there? So when you go to this illustrative mathematics website, there are videos that show students solving this problem and other problems using an approach that reflects the knowledge and skills as described for this particular one in grade 4, Operations and Algebraic Thinking, standard number 3, if you're in the Common Core standards. And then another student is solving this exact same problem, but as it relates to the knowledge skills in 8th grade, Expressions and Equations, standard number 8. In both cases, in both videos, the students move fluidly between the context and the mathematics and then back again. I encourage you to watch these videos to see the students reasoning abstractly and quantitatively, and they're fun to watch. Another sample task that I chose comes from the website Achieve the Core, to get your students to reason abstractly and quantitatively. So earlier you heard me talk about those two buzzwords, contextualize and decontextualize. Contextualize means taking the abstract mathematical representation and putting it into a context, and decontextualize means taking the context and representing it abstractly. Students need to move between these representations fluidly and use them to manipulate and understand the relationships between quantities. This idea relates primarily to abstract reasoning, but don't forget quantitative reasoning. While engaging in quantitative reasoning, students pay attention to the meaning of quantities they compute and also the units that are involved. Obviously, instructional materials for different grade levels will have some commonality in opportunities to engage in practice number 2. However, the complexity of the problems will increase, as well as the depth at which students are expected to connect the quantitative and the abstract reasoning. So you can see from my example, it's a grade 2 example. Students need to decontextualize the problem to write 53 plus 34 equals a blank, showing that abstract reasoning. Then they also need to attend to the fact that the result they get, 87, is actually $87. Another example from the Achieve the Core website that I chose was for 7th grade. As you look at this example, you will see students engage in many of the same skills related to practice number 2 as they do in the earlier grades. Again, students are decontextualizing the problem, producing a symbolic representation, manipulating those symbols, and then putting it back into the context. We see that students are being asked to make sense of their abstract solution in context. Additionally, we see the need to repeatedly move between context and accurate abstract representations. And another task from Achieve the Core. This task is for high school students. You will see students begin to deepen their understanding of various parameters and how changing those parameters changes the situation. And you can find all of these at achievethecore.org. Questions you would want to ask your students that relate to mathematical practice number 2 could include, what do the numbers in the problem represent? What is the relationship of the quantities? How is blank and related to blank? What does this mean to you? What does this symbol mean to you? What does this quantity mean to you? What properties might we use to find this solution? How did you decide in this task that you needed to use a protractor? And could we have used another operation or property to solve this task? And then ask why or why not. Moving on to mathematical practice number 3, construct viable arguments and critique the reasoning of others. Mathematically proficient students analyze problems and make conjectures using data. They justify their conclusions and communicate them to others. They listen to or read the arguments of others and ask useful questions to determine the rightness of those arguments. Students are able to explain their thinking for the solution they found, use accurate vocabulary in their explanations, and justify and explain why their solution is correct. They also can understand and discuss other ideas and approaches. This practice asks students to develop reasoning and communication. Problems that can be solved with only one routine step give students no chance to assemble a mental sequence or argument, even non-verbally. The inclination to justify their conclusions also depends on the nature of the task. Certain tasks naturally pull children to explain. Ones that are too simple or routine really feel unexplainable. Depending on the context, I added can seem to a child hardly worth saying. The skill of communicating or justifying to others comes from having plenty of opportunities to do so. The way children learn language, including mathematical language, is by producing it as well as hearing it used. When students are given a challenging task and allowed to work on it together, their natural drive to communicate helps develop the academic language they will need in order to construct viable arguments and critique the reasoning of others. So as teachers, we should provide all students opportunities to understand and use assumptions, definitions, and previously established results in constructing their arguments. We should provide ample time for our students to make conjectures and build a logical progression of statements to explore the truth of their conjectures. As teachers, we should provide opportunities for our students to construct arguments and critique the arguments of their peers. We should facilitate and guide students in recognizing and using counterexamples. We should encourage and facilitate students to justify their conclusions, communicate and respond to the arguments of others, and ask useful questions to clarify and or improve students' arguments. We should expect our students to make conjectures and explore the truth of those conjectures, recognize and use all counterexamples, or counterexamples, maybe not all, justify and defend all conclusions and communicate them to others, and recognize and explain flaws in their arguments. So, for example, after listening or reading the arguments of others, a student could respond by deciding whether or not the argument makes sense. They can ask others useful questions in order to improve arguments. This sample task comes again from Illustrative Mathematics. Mathematically proficient students understand and use stated assumptions, definitions, and previously established results in constructing arguments. They make conjectures and build a logical progression of statements to explore the truth of their conjectures. They are able to analyze situations by breaking them into cases and can recognize and use counterexamples. They justify their conclusions, communicate them to others, and respond to the arguments of others. They reason about data, make plausible arguments that take into account the context from which that data arose. Mathematically proficient students are also able to compare the effectiveness of two plausible arguments, distinguish correct logic or reasoning from that which is flawed, or if there is a flaw in an argument, explain what that flaw is. Elementary students can construct arguments using concrete reference such as objects, drawings, diagrams, or even actions. Such arguments can make sense and be correct even though they are not generalized or made formal until the later grades. Later on, students learn to determine domains in which an argument applies. Students at all grade levels can listen to and or read the arguments of others, decide whether that argument makes sense, and ask useful questions to clarify or improve the arguments. This particular example is a grade 2 example in which students explain how they know that 23 plus 2 is the same as 2 plus 23. There's a video of students solving this problem on the Illustrative Mathematics website. If you just go to the practice standards and search for mathematical practice number 3, grade 2, you'll find the video of how students are solving this problem. Questions to ask that will develop mathematical thinking related to practice number 3 are what mathematical evidence would support your solution? How can we be sure that? How could you prove that would work? Will it still work if I do this? What were you considering when you did that strategy? How did you decide if that strategy, how did you decide to try that strategy? And how did you decide what the problem was asking you to find? Could you demonstrate a counterexample? What's the same and what's different? So you noticed I used a lot of examples, or several examples, from the Illustrative Mathematics website. If you just go to illustrativemathematics.org/practice-standards, you'll see a list of the 8 standards for mathematical practice, and you click on that side menu and it will take you to examples, videos, practice task. I would encourage you, if you haven't looked at that site, to get familiar with that site. Another great site that I found was the Mathematics Assessment Project at map.mathshell.org. There are many tasks here that relate to multiple standards, and a lot of these are at the high school level and middle school level, but I did find it seemed like more at the high school level. And a lot of these, when you click on one, like the first one, optimizing coverage, that could relate to practice number 1, number 4, number 6, and number 8. So I would encourage you to look at that site as well. Some other sources that I wanted to share with you if you haven't found them. Since I'm in Kansas, I'm very pleased to share with you the Kansas Flip books. Even if your state is not a Common Core state, these are good to use. They give good sample tasks. They give mathematical practices. They give tasks related to a particular standard. So I would encourage you to look at the Flip books. Bill McCollum has a blog that I would encourage you to look at. Be sure and look at, if you haven't already, the U-Cubed website by Joe Bowler. Debbie Wagner also has some really cool math practice standards, sample task, and some posters that you could find useful in your classroom. And then again, Inside Mathematics. Thank you very much for your attention. If you have questions, you could email me at jkstramel@fhsu.edu. I appreciate your time. Thank you very much.